Grade 12 Physics, Energy and Momentum Note number 2, Hooke's Law. In this note, we're going to actually look at how spring expands and take a measure of the force it's going to deliver when it expands or when it compresses. This is something called Hooke's Law, named after physicist Robert Hooke. So let's say here we're going to hang a weight from a spring that's attached to the ceiling. We're going to examine the spring and how much force it's going to deliver as it either compresses or extends. So there's our mass hanging from the ceiling with the spring connecting. Gravity is going to pull it down, but that spring is going to restore it. It's going to come to rest with some force of the spring pointing upwards. There's going to be an extension of the spring, which we're going to call X. So that system there is in equilibrium, it's at rest. So let's say we hung different masses on that spring and we measured different extensions according to whatever the mass was. So let's say that information is given in the table. We can make a graph of the data. The force is the force of gravity pulling that weight down, and the extension is just that how far the spring stretches in meters. So we can graph each of our points. That point, by the way, should be actually one step higher. I'll recognize that at the end. We start to notice a little bit of a pattern on this graph. All the points seem to be in a straight line. So we can put a line of best fit right through them. And we realize that as a spring stretches, it's going to have a linear relationship with force. So if that spring doubles in its stretch, we're going to have a doubling of the force it's going to deliver. And the same is true if the spring compresses, we'll get the same force delivered if it compresses the same distance as it was stretched. So what we can do is we can make a relationship for between force and extension based on that linear line on the graph. So if it's linear, we can use from grade 9 math, y equals mx plus b, where on our y-axis we're measuring a force, on our x-axis we're measuring extension, which we use the variable x, and our y-intercept was 0. Here's the slope of the graph. The slope is basically describing the stiffness of the spring. So if the slope is steeper, so is the stiffness of the spring would be a lot stronger. If it was more shallow, it would be less stiff. And we give that variable k. So that gives us the formula F equals kx, where F is force in newtons, k is something we call the spring constant, which is that stiffness. It's measured in newtons per meter. And x would be the extension or the compression of that spring measured in meters. If we take a look at the units to make sure they work, the left side here would be newtons, the right side newtons per meter multiplied by meter, and they check out. The meters will cancel. We can also actually calculate the energy stored in a spring, which would be a potential energy. If you stretched a spring or compressed it, the spring has the ability to do damage. That formula would be 1/2 kx squared. So very similar to the force formula, except here there's a half term and the extension is squared. If we look at these units, the left side is in joules, the right side newtons per meter times meter squared. That will get us newton meters left over. Now that is equal to a joule. If we remember W equals FD, that would mean joules is equal to a newton meter. So it's important not to confuse the force of a spring with the energy stored in a spring. Force for sure is not an energy. If we look at the different properties of these equations, if we look at F equals kx, as x increases, F will increase proportionally. So that means if x is doubled, the force is also doubled. But for energy, we have a bit of a different relationship. If x is increased, the energy will increase exponentially. So that means if we stretch our spring, if we double that stretch, the energy will quadruple. Next here, as K increases, if we increase the stiffness of the spring, F will increase proportionally. If we look at the energy formula, energy will also increase proportionally. So let's do an example here. Let's compare force and energy in a spring with a K constant of 456 newtons per meter. And let's say we stretch that spring a distance of 2.4 meters. First, we're going to calculate the energy stored in that spring, where E equals 1/2 kx squared. We're going to put our numbers in, 1/2 times 456 times 2.4 squared. That gets us an energy value of 1,310 joules. Now force, we're going to calculate something different, where F equals kx. So K here is 456, X is 2.4 meters. That gets us a total force of 1,090 newtons.